بسم الله الرحمن الرحيم. Assalamu alaikum wa rahmatullahi wa barakatuh. This is the last experiment of this semester, and in this lab we will study fluids. So just to give you a short motivation, I'm sure you have seen this picture before. This is a picture of a floating iceberg, and as you can see, the part that is submerged under the surface is much larger than the emerged part above the surface. Is this always the case, or sometimes we have the reverse situation? We will see, or hopefully we'll answer this question, and you will be able to answer this question in the using part A. So in part A, we'll determine the density of a solid floating on fluids with variant or with various densities. So recall that for a floating object, it will be at equilibrium if the weight of the object equals to the buoyant force that acts on the object from the fluid. And this buoyant force, we know the weight of the object, simply in the mass of the object times g. But the buoyant force is the weight of the displaced fluid. And this displaced fluid is given in this case by this submerged part of the cube. So the mass of this submerged part times g gives us the buoyant force. And here we see it mathematically. Now there is an important quantity that is of concern in this part, which is the relative area. Now notice that this cube is in contact with the fluid in 5 areas, or in 5 surfaces. We have 4 lateral faces, so to speak, 1, 2, 3, 4, and 1 on the bottom, so a total of 5. So the relative area is defined as the area that is in contact between the object and the fluid to a square, as you can see here. So the relative area is the area that is in contact between the cube and the fluid divided by the face area of the cube. And this area is a square from the face on the bottom and 4xa, which is the area of each of the lateral faces. Alright, so by the way, A is the side of the cube. So we assume that the cube is of side A. Now we can simplify this equation to obtain the following relation. 1 plus 4 times the volume of the fluid divided by the volume of the object. We can also get the height of the fluid divided by the height of the object, but we'll use the volume because it's given in the experiment. Now we can also write it in a different way using the densities. However, note that the density is inversely related to the volume, so this fraction will be flipped. Good, so let's go to the simulation. And let's note the data that we have. My data says that the object density should be 1.2 and the fluid density should be 1.3. And again, we have to fill in a table. So in the simulation, we can control the density of the object using this cursor, and also we can control the density of the fluid. So my data says that the density of the object should be 1.2 and of the fluid to be 1.3. Then click run. Of course, you can increase the speed of the animation. Now, as you can see, we have the volume that is above, but we do not need this quantity. We'll only focus on the volume that is below. So record this data in the table that you are given. So the density of the fluid is 1.3. The volume of the fluid in centimeter cubed is 920. Here it says it's 0.92 times the volume. This is the volume of the cube. But as you can see, the volume of the object is 1000 cubic centimeters. So simply multiply this number by 1000 to get the volume of the fluid in centimeter cube. Alright, then do not touch the density of the object, but change the density of the fluid. So I'll change it by 0.3 to 1.6. Okay, then take the measurement again, take the volume of the fluid again. So in my case it's 750 cubic centimeter, as you can see, and repeat the process with different densities of the fluid. So you can think of this experiment as changing the fluid that is here from water, for example, to mercury, to different fluids. Okay, after that, after completing this table, copy it and take it to Excel, and we'll make a plot of A versus 1 over rho F. And by the way, A, just to remind you, is given by this equation: 1 plus 4, the final volume divided by the volume of the fluid divided by the volume of the object. And we will not use this equation because we will get the density of the object using the slope. Okay, so copy this table, go to Excel, paste, now sorry, it's messy, but it's 1 divided by rho of the fluid. So equals 1 divided by rho of the fluid. Do the same for the rest. Now the relative area equals 1 plus 4 times the volume of the fluid divided by the volume of the object, which is 1000. Do the same for the different volumes. Alright, you can also change this number of figures, and we are asked to make a plot of A versus 1 over rho of the fluid. So select the two columns, do not select the title, sometimes it makes mistakes. Click insert. Now as you can see, it's a good linear relation. Just to make sure, we are asked to make a plot of A versus 1 over rho final, and these values indeed are on the y-axis, and these values are indeed on the x-axis. And do not forget to make this plot appropriate. Change the title and the axis, and also add a trend line. And what else do we have? Again, the same procedure, questions about the slope and what does it represent. Then you have to find the density of the object using the slope. And also one more discussion question: what would happen for the object if we take the density of the fluid to be infinity? What do you think would happen? And you can also answer this question, or we have to look at equation 3 to discuss also the relative area. Now in part B, we'll use a different simulation and different mechanics, because in part A we discussed fluid statics, but in this case we'll discuss fluid dynamics, and we'll use Bernoulli equation basically. So in this part we have a hole in a bucket, okay, and of course we have a stream of fluid, and we can consider this stream to be an ensemble of small infinitesimal droplets, where each droplet follow free fall motion, or you can think of this motion as a projectile motion if you like. So I'd like to study the relation between the height of the hole and the range of the stream. Alright, so there is a simple derivation that you are encouraged to see and to look at the appendix, and it should be a good exercise for you to prepare for the finals as well. So I encourage you to look at it. And in this case, this is the velocity of the fluid that is emerging from the opening, and simply given by 2 times g times h, where h is the distance measured from the top. Alright, in the appendix you can see you can obtain this relation as well, where the range is given by 2 times the square root of h times L minus h. L in this case is the height of the bucket, and it's fixed to 200 centimeters. So let's go to the simulation. From here you can control the height of the hole, and you can observe that the range changes with changing the height of the hole. So let's read the data that we have. We'll start from, at least in my case, with h equals 10 centimeters, sorry, and we will increase it by steps or increments of 30 centimeters. Okay, so starting with 10 centimeters, take a measurement of x. Notice that the range is called here x. So for 10 centimeters, we take it in meters, and also for the range, it is 0.1 meters, and the range is 0.872 meters. Then increase it by 30 centimeters to 40. The r, or the range, is 160 centimeters, or 1.60 meters. Again, and do the same for the rest of the height. Take a measurement of the range. Then this z is simply defined as the square root of h times L minus h, where L is 2 meters. So copy this table, and we will make in this part two plots. The first plot is r versus h, and the second one is r versus z. So go here and paste. So this z is equal square root of h times L, which is 2 meters, minus h, close the brackets. Of course, you can reduce the number of figures. Now the first plot will make it between r and h. Now notice that it is indeed nonlinear, which is expected, but is it r versus h or h versus r? As you can see here, the maximum is 2.5. Yes, very good. We can see that this plot is of r versus h, and you can see that it is nonlinear. We are asked to include this plot in the, of course, after refining it and adding the title and the axis labels. We do not have, of course, in this case, to add the trend line. Now include this plot and record the value of h for which the range is maximum. Okay, then you can also obtain this value numerically, and this is an optional part, using the equation 5. Now we also make a plot of r versus z. We can see that the points fall on a straight line, but notice that we want to make a plot of r versus z. So this axis should be r, and this axis should be z. Is this the case? No, it is reversed. As you can see, the maximum on this axis is 1, which is z. So this axis is z, and this axis is r. So click on the data, select data. The x values should be z, and the y values should be r. Okay, then do the same procedure, add a trend line, and change also the title and the names of the axis. Okay, what's the slope? What does it represent? Is it what you expect? And also, this is a discussion question, that the time that it takes for a droplet to fall from the hole is given by this relation. What would happen if g goes to 0? Now in the last part, we will not do a new experiment. So you can think of it as a continuation of the previous part. Now we did not tell you, it was hidden, but in deriving this equation, which is the velocity of the fluid that is emerging from the opening, we assume that the velocity of the surface is 0. So in part C, we will assume that this value is not 0. So you will end up with a correction of this formula in part C. Now the continuity equation says that the cross-sectional area of this bucket times the velocity of this surface equals to the velocity that is streaming out of this hole times the cross-sectional area of this hole. Okay, so you have to follow and also by Bernoulli equation, you can get this equation of the relation between the fluid, between the top of the fluid and the fluid that is emerging from the hole. Now we have to eliminate V using equation 8 and 7, and you have to express V0 in terms of Hg, A, and A0. So just to give you a hint, again, you will get an equation that is similar to this equation, but with something in the denominator that is a correction factor of this equation. Alright, after that you have to calculate for certain parameters the values of V0 using the equation that you derived here, and using the equation with no correction, that is V0 equal square root of 2gh. After that you have to answer this question: what do you conclude about the approximation that we made? Is it good or not good, or what do you think? So this is it, and of course do not forget to make a conclusion about this lab. Good luck.